Hey, welcome you guys. Yeah, so this is my last video about introduction of the real analysis. So all this video is to prove this Riesz Fischer theorem. Yeah, so previously I already introduced the L2 space, and basically it's the complex analysis on the back measurable. So you're using the back measurable to get something very interesting space called L2. So L2 space, let me just quickly remind you. So L2 space basically just this, right? So F belongs to L2 space if F is measurable and its square on X is finite. Okay, so and then previously we proved something like Cauchy-Schwarz, and then we proved that L2 space is the continuous function stands in the L2 space. Okay, so this video, our goal is to prove Riesz Fischer's theorem. And then you can follow the routine chapter 11. Okay. Basically I just follow the routine. Okay, hope you guys subscribe to my channel. Okay, so before we do this, let me just talking about the famous results. Basically it's L2. L2 is complete. It's a complete metric space. Okay, so let me just quickly give a definition. Also, let's say F at the Fn belongs to, let's say, L squared, so L2. Let's say n from 1 to 2, and we say that Fn converge to F in L squared in L2. So this is the word. We say that Fn converge to F, not pointwisely. We say Fn converge to F in L2 if the norm Fn minus F goes to 0. Okay, so remember the norm of F is defined to be F squared d mu x. Okay, and we say Fn is Cauchy. Okay, so remember in the analysis, in the usual analysis, we say Cauchy is that for epsilon greater than 0, there is this some positive number. Let's say this is, let's say, using large n, such that when n m greater than n. So in this case, what we need to use is L2 norm, right? So we have Fn minus Fm less than m. Okay, so this is the definition. Okay, so we say L squared is complete. So theorem. If Fn is Cauchy, let's say if Fn is Cauchy, so it's complete. It's complete, right? So this means what? This means that it's Cauchy in L2 square. There exists the function f in L square u, such that Fn converge to f in L square u. So which means that Fn converge minus f is less than epsilon. There exists f and such f in the L square u. So this is the this is just saying that L square is a complete metric space. This is a famous result that if you study a real analysis or something, you always hear about the people talking about this kind of fact. Okay. So let's follow the proof. Okay, so since the proof. Okay, we know that what? We know that Fn is a Cauchy, right? So let's say Fn is Cauchy. And so we know, right? So we can find a sequence, we can find a subsequence, let's say nk, such that Fnk minus Fnk plus 1, right? So since it's Cauchy, right? So I can make this guy arbitrarily small. Let's say I make it 1 over 2k, okay? K from 1 to 2 to 3. And I do a summation. So let's say I pick any function g, which is L squared u. So by the Cauchy-Schwarz. Don't worry, this proof is not difficult. I mean, conceptually. In analysis that you need to write down everything, so not so difficult, but conceptually it's easy. Okay, so you have this, right? Cauchy-Schwarz, and then you take summation from k from 1 to infinity. So this guy will give you what? Will give you g, right? So since g is in L2, so this guy is finite. Okay, so what we have done is that we get something very strange expression. Let's say given any L, given any G, given any G, right? So sometimes somehow like I prove this. Okay, so this is very weird expression. And then this is non-negative, right? So we can bypass this. This is a monotone convergence theorem. If you haven't seen this, then you should go to my previous video about Factor's lemma and the monotone convergence. So this is a monotone convergence. So since it's finite, right? So what we have, what we can say is what? What we can say is that this guy is finite. Almost everywhere, right? Almost everywhere. Okay, this is simple, right? The reason is that if it's not finite, right? If this is the non-finite part is non-zero measure, then it will blow up. So it's almost everywhere. Okay, so by a wire truss M test, right? By an M test, right? So these guys less than infinity. So M test means that let's say if I consider k from 1 to infinity, consider fn k plus 1 minus fn k. This guy will converge almost everywhere. Because this guy is almost everywhere. So by wire truss M test, this guy will converge almost everywhere. So this guy will converge to what? Let's say partial sum of these. Right? Let's say partial sum. So suppose maybe this is let's say m. Okay, so this is fn m plus 1 minus fn 1. Okay. So obviously that okay. So this converges almost everywhere, right? So I can define f. Okay, so I can define f of x to be what? To be limit fnk, right? So this is a partial, this is the subsequence. So I get nk goes to infinity. And then this guy converge, right? By this reason. Okay, so this f of x exists almost everywhere. Okay, and so I don't care about what the other points, right? Because when I do the integration, I don't care. That point has measure 0. Okay, so my claim is that I want to claim that f is what we want. So my claim is that f of x is what we want. What we want to prove that is complete, right? So I claim that f has what the property that I want to, which is fn minus f goes to 0 as n goes to infinity. And also f belongs to L squared. L squared. Okay. This is simple, right? Because let's consider f minus fnk. Right, so let's say if somebody gives you epsilon greater than 0, and then you choose nk greater than n, then you consider f minus fnk, and this is what? This is just f minus fnk square d mu x, and then go. So now I use a Factor's lemma. Okay. I use Factor's lemma, so this guy's less than or equal to limit if t goes to infinity, fni minus fnk goes to infinity. I should say I. So this is the Factor's lemma, right? Because when limit I goes to infinity, this guy become f, right? So I can use the Factor's lemma, and this guy is bounded, right? Let's say epsilon, right? Because this guy is cosy. Okay, so when I choose nk greater than n, then any ni minus nk, two knowns, is bounded by epsilon. Okay, so now what we have shown is f minus fnk is L, f minus fnk for large enough k belongs to L squared. And we know that f is f minus f and k plus f and k, right? So by the trigonometric inequality, this guy belongs to L2, right? But by large enough k, this guy can be arbitrarily small. So f belongs to L2. Okay, so what we have already showed is, okay, the rest is just showing for any n, fn minus f can be arbitrarily small. So the remaining is to show, let's say, fn minus f. And this is trivial, right? Because you just find something which is large enough. So, okay, so this, sorry, this is n. Okay, so this term is bounded by these two. And this is by definition, right? This is, as I say, right? This guy can be arbitrarily small. How about this guy? How about this guy? So this guy is fnk minus fn, okay? And this guy can be bounded by the just what we just write, right? So it can be bounded by the cosine, okay, right? We'll take large enough nk, then every n greater than nk, fn minus fnk can be bounded, right? So this is just the straightforward cosine definition. So bounded. So we prove this. Out. Okay, so famous results. L2 is a complete metric space. Okay, so theorem, our final theorem in the introduction of the real analysis. So Riesz Fischer. Okay, so notation is that phi n be also normal basis. Also normal basis on X. And suppose you give me some Cn for C1, C2 up to infinity, which is converge. And let's say you define Csn to be summation of Ci phi I, say I from 1 to n. So this is all the definition, or you just write down. Then, and this is very amazing, right? So suppose I give you some also normal basis, and you define some summation which is finite, and this is Sn. And you can see that then the theorem says that there exists a function f, which is L2. Is L2, not just L2, by the way. So sometimes I use this, sometimes I use this. So this is the same notation. So such that Sn converge to f in L2 square. So this is the first amazing part, that you can find something which is really L2, and your Sn partial sum really convert to such f. And what? And also, so this is the first part. And the second part is that f is this is notation. Let me just explain. Okay, so this notation means that Cn is actually f phi n bar dx mu. Sorry, dx mu. Okay, so this is you can say that f is I should say Sn is a Fourier coefficient of f. Sorry, Cn is a Fourier coefficient of f. Okay. Okay, so let's give the proof. So I will leave you guys to think how amazing this theory. Try to appreciate. Okay, so let's consider Sn minus Sm. So by definition, this guy is Cm plus 1 up to Cn squared. So let's say if m, let's say n greater than m. Okay, so this guy converge, right? So this guy converge. This guy can be arbitrarily small, right? Because this guy converge. So which tell you that Sn is cosine. Okay, so by the previous L2 square, U is complete. So there is this smart guy, which f L square U, such that the Sn converge f. Okay, so this is really beautiful that we prove the first part. and basically we prove everything. So this is the remaining. Yeah, very quickly. Okay, so and we know that this Sn minus f, right, goes to 0. Okay, so rest is just to prove the coefficient. So let's consider f phi k bar d mu x is a minus ck. So I want to show they are the same, right? So I want to bound this. So let's say this is f phi k bar d mu. So the ck is just the notation, just the s, right? So s phi k bar. Let's say sorry, Sn phi k bar d mu x for n greater than k. Right, so this ck is just the coefficient of this, right? You can just using the orthogonality of the phi. Okay, so your f phi k bar d mu x minus ck by Cauchy Schwarz, our lovely Cauchy Schwarz. It's just this. Okay, by this one. You just take out your phi k bar. Okay. And this guy is arbitrarily small, right? Because this guy is bounded. This guy is 1. Okay, and this guy it's not 1 now. It's 1, right? Because it's also Gomo. And then this guy is arbitrarily small, right? So if you take n to be large, so take n to be arbitrarily large. Be arbitrarily large. Okay, so ck is just this. Okay, so we proved the theorem. Okay, so let me just say something finally. So let's write down another definition. So when we say that phi n this also normal set is complete, so let's say this is also normal set is complete if the following is true. If f phi n bar d mu is 0 for every n, let's say, so if for every f, so if for every function which is L2, and this guy is 0 for every n, implies no, this is the definition. So definition means that somebody give you any L function, L square function. If it's all the Fourier coefficient of this f is 0, then this function must have the 0 norm. Okay. This is the definition. Okay, so we got our final theorem. This final theorem says what? Says that let's say phi n is also normal and complete, and if f belongs to L square mu, and if f has this Fourier coefficient Cn phi n and from 1 to infinity, then if you take absolute square, so you got some of this. So this is the Parseval's theorem. Okay, but the proof is different. Okay, so proof. So you can first using the Bessel's inequality and show that Cn square converge, and then you do the same thing, right? You just define Sn to be Ci phi I from 1 to n, and this is Cauchy, right? So there is the function g. Right, sorry, you use these Riesz Fischers, right? So there is a function g L square, such that g realizes all these coefficients, right? So such that g has the Cn phi n and from 1 to infinity. Okay, and by simple computation, I know that Cn square is a summation Ci square I from 1 to n. So compare these two, right? I get the g square, g norm. Yeah, g norm is a summation. G norm square is a summation of these. Okay, so this is a Riesz Fischer. Okay, and but you will say, what the hell is what's the relation to f? Right? So I just say that there's some guy which is 3g, but remember that the function is complete. So if I use f minus g, I approximate to 0, right? Because every further coefficient of f minus g is 0, which tell you that the norm of f minus g is 0. And the norm of f minus g is less or is greater or equal to f norm minus g norm and take absolute value. So which tell you that the f norm and the g norm must be the same. So f norm will be the same as this. Sorry, the f norm square will be the same as g norm square, which is the summation of cn square. Okay, so final results. I just want to tell you that so if in L2 square you have f and g, they have the same Fourier coefficient. In a complementary space, then the set A x f of x not the same as g of x is measure 0. The reason is that the norm of f minus g squared is 0. Okay, so any square function which is 0, then by previous proof, the non-zero part, the non-negative part, sorry, if you have a non-negative function which integration is 0, then the non-zero part must be measure 0. Okay, so this is the final results. Okay, so we finished all the Ruding's textbook, and then we move to Sigma in the future. And I may go back to fill some Galois theory or something like some general relativity, just my own interest. See you guys next videos.